In this video, we use Hund's rule and the Aufbau principle to generate electron configurations for atoms containing a large number of electrons, and we also introduce the idea of a condensed form of an electron configuration. Now this here is the general orbital diagram for a multi-electron atom, which basically includes all elements except for hydrogen. Now all atoms in their ground state, which means the lowest possible energy arrangement of the electrons around a nucleus. So all atoms in their ground state show a well-defined configuration of electrons and a distribution of electrons between the available shells, subshells and orbitals. And they do this while still obeying the Pauli exclusion principle. So, for example, a ground state hydrogen atom always has its single electron occupying the 1s orbital, and its electron configuration is 1s1. A ground state lithium atom always has its two of its electrons paired in the 1s orbital and the other electron in the 2s orbital. Electron configuration 1s2, 2s1. And a ground state carbon atom, which has 6 electrons in total, has 2 electrons paired in the 1s orbital, 2 electrons paired in the 2s orbital, and 2 electrons occupying 2 of the 2p orbitals with their spins parallel, meaning they have the same spin orientation, either both spin up in this case or both spin down. So using these orbital diagrams, it's possible to identify the properties of each electron in any atom. For example, we can identify the spin characteristics of each electron, whether they're spin up or spin down, or spin up in this case here for this electron in the p orbital, or spin down in this particular electron in that 2s subshell there. We can identify electrons of low energy or high energy. For example, these 2 electrons down here in the n=1 shell have relatively low energy compared to the other electrons. We can identify electrons with a spherical distribution around the electron. For example, these 4 electrons all exist in s subshells, meaning they have a spherical distribution around the nucleus. We can identify electrons with a dumbbell distribution around the nucleus. For example, these 2 electrons in the p subshell have a dumbbell distribution around the nucleus, and we can also identify the orientation of that distribution. For example, this electron is orientated its dumbbell shape around the x-axis and this one around the y-axis. And we can basically do this for all electrons in any atom of any element. And we can also represent these orbital diagrams in a slightly different way. So here are the orbital diagrams for the first 10 elements, and what we see here is the 1s, 2s and 2p subshells are shown on the screen as being level. Now we know that the energies of these subshells are not equal, and this way of representing orbital diagrams is not attempting to display the relative energies of the orbitals. And orbital diagrams are often shown like this, as they are much more efficient in terms of how much space they take up, because as you can see here, we can fit 10 orbital diagrams on the single screen here. What you can also see here is how the number of electrons build up in a very well-defined distribution or configuration between the available orbitals, subshells and shells. The other important information on this screen is the list of electron configurations for each element, and the electron configuration is a shorthand statement of how many electrons occupy each subshell in an atom, and it's a shorthand way of representing the orbital diagram. Now, electron configurations use the subshell designation combined with superscripted numbers. So the subshell designations being the 1s, 2s, 2p, 3s, 3p, 3d, etc., etc., and they are combined with superscripts to be able to identify exactly how many electrons are in each subshell for a particular atom in its ground state. So for example, we can look at the element fluorine, 1s2, 2s2, 2p5. So that means that we have 2 electrons, the superscript 2, associated with the 1s, 2 electrons in the 1s subshell, 2 electrons in the 2s subshell and 5 electrons in the 2p subshell. And the addition of all the superscripts, 2 plus 2 plus 5 equals 9, is the total number of electrons in that fluorine atom. Now, we've seen how orbital diagrams can be successively built up to generate ground state electron configurations of atoms, and this building up principle, otherwise known as the Aufbau principle, involves successively filling orbitals in a specific order. And that order is principally governed by filling lowest energy orbitals first. No more than 2 electrons can fit into a single orbital, and those spins of those 2 electrons in a single orbital must be paired. There must be one spin up and one spin down in order to not break the Pauli exclusion principle. And for orbitals in the same subshell and therefore having the same energy, we need to follow Hund's rule. And Hund's rule, the lowest energy arrangement of electrons in a subshell is obtained by placing electrons into separate orbitals of the subshell first with the same spin prior to pairing the electrons within orbitals. So what do I mean by that? We have the electron configuration of carbon shown here, 1s2, 2s2, 2p2, and we can see that the 2 electrons in the 2p subshell there are spin paired. I can add another electron. Sorry, they were spin parallel, both in the same direction. I can add another electron, so that I've got 7 electrons, and we see the 3 electrons in the 2p subshell there are all spin parallel. They're all in the same direction, and we get the electron configuration for the 7 electron nitrogen atom there. Add an 8th electron to give me the electron configuration for oxygen, a 9th electron to give me the electron configuration for fluorine, and a 10th electron to give me the electron configuration for neon. 1s2, 2s2, 2p6, remembering that 2 there represents the 2 electrons in the 1s subshell, that 2 representing the 2 electrons in the 2s subshell, and that 6 superscript there representing the 6 electrons in the 2p subshell. And that the sum of those 2 plus 2 plus 6 equals 10. That equals the number of electrons in the atom, in this case, neon. So, what happens though as we progress through elements and work our way up to larger and larger numbers of electrons? Because it may start getting confusing as to which orbitals and subshells need to be filled first, because we already know that the 4s subshell is actually at a lower energy and is filled before the 3d subshell over on this side. And also, as we get to higher and higher energy levels, the energies of the subshells get closer and closer together, and it can get quite confusing as to which subshells to fill first. And so what we can use is a simple diagram, a mnemonic diagram called the Aufbau diagram, and we use it to remember the order of filling of shells. And what we do is we start by writing out the subshell designations at each level, starting at n equals 1. And we also need to remember the order of subshell designations, S, P, D, F, as we go from left to right across the page. So we start by writing out 1s on the first line. And above it, we write 2s and 2p, representing the 2 subshells that exist at the n equals 2 level. Above it, we write 3s, 3p, 3d. They are the 3 subshells that exist at the n equals 3 level. Above it, 4s, 4p, 4d, 4f, and so on. 5s, 5p, 5d, 5f. We won't need to go to 5g, you'll see in just a moment. 6s, 6p, 6d should be enough for us, and then finally 7s. So we write these out as subshell, all the available subshells that are available in each of the energy levels on separate lines. And the order of subshell filling is now gained by drawing 45-degree lines back through each of these subshell labels here. And so we start by filling subshell 1s first. It's the lowest energy orbital. We then fill the 2s subshell. We then fill the 2p subshell, followed by the 3s. We come back and we fill up the 3p subshell, and then notice we fill the 4s subshell before coming back to fill the 3d. So the 4s is lower in energy than 3d. So fill up 3d, 4p and 5s. And again we fill in the 5s subshell before filling in the 4d. Then we go to 5p and 6s. And so you can see now the 5p and the 6s subshells are actually filled before the 4f. So the 4f is actually higher in energy than the 5p and the 6f. So we fill 4f, 5d, 6p, 7s, and then finally 5f and 6d. By the time we get to this level here, we've exhausted all the elements in the periodic table. We've gone up beyond 92 electrons, which represents the uranium atom, which is the last of the naturally occurring elements. Now the other thing that we need to remember here is the number of electrons that each subshell can accommodate. So for example, there is only one orbital in any of the s subshells, and so s subshells can only accommodate 2 electrons. In the p subshells, 3 orbitals exist. Each one can accommodate 2, and so p subshells can accommodate 6 electrons. There are 5 orbitals in the d subshells, so they can accommodate a total of 10 electrons, and there are 7 orbitals in any of the f subshells, and they can accommodate a total of 14 electrons. So let's use the Aufbau mnemonic diagram to generate the electron configuration for bismuth, which has an atomic number of 83 and therefore contains 83 electrons in the neutral atom. Now bismuth is located on the 6th period in group 15 or group 5a of the periodic table. And basically, if we're able to generate the electron configuration for bismuth using this approach, we'll be able to generate the electron configuration for any element. So what we're going to do is we're going to start by filling in the 1s subshell first, and we know that 2 electrons can fit in the 1s subshell, and that represents a designation of 1s2. So there are 2 electrons there, and our cumulative total of using up electrons is 2. The next one we're going to fill up is the 2s subshell. Now that's a 2s2 because there are 2 electrons that can be filled up, and so our cumulative total now is 4 electrons in total. Remembering we're counting up to 83 in the case of bismuth. The next ones we fill up are the 2p and the 3s. Now the 2p can accommodate 6 electrons, 2p6, and the 3s can accommodate 2 electrons. So that's 3s2. So there we go, 2p6, 3s2, a total of 8 electrons, and a cumulative total of 12 electrons used up so far. We then go to the 3p and the 4s. So that's 3p6 and 4s2, again a total of 8 electrons and a cumulative total of 20 electrons out of the 83 used up so far. We go to 3d, 4p and 5s, so the d subshell can accommodate 10 electrons, that's 3d10, 4p6, 5s2, so 3d10, 4p6, 5s2, a total of 18 electrons, and we have a cumulative total now of 38 electrons used up, remembering we've got to get to 83. The next set of subshells we fill up in order, 4d, 5p, 6s, so that's 4d10, 5p6, 6s2, and again a total of 18 electrons there, and we've used up 56. We're now going to start filling up the first of our f subshells, so 4f, that subshell can fit 14 electrons. The 5d can fit 10 electrons, so there's 24. So we're getting pretty close to our number of 83, and it turns out that we only need to put 3 electrons in the 6p subshell to get to 83. So 4f 14, 5d 10, 6p 3, a total of 27 electrons, and we've got to our total of 83, remembering we have to stop at 83 in this case for bismuth. So the overall electron configuration then is just putting all of these together. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f15, 5d10 and 6p3. So much for it being a shorthand notation. It is still a shorthand notation relative to drawing out the full orbital diagram. And the full orbital diagram filling in 83 electrons would look very, very messy indeed. We can condense this long electron configuration, and we'll see how to do that right now. So what we've got here are the electron configurations just for elements 11 through to 20. And you can see that even when we get to element 20, let alone element 83 like bismuth is, that the electron configuration is actually quite lengthy. Now what we can look at in all of these electron configurations is the fact that they all share this common beginning, 1s2, 2s2, 2p6, and we can see that that is actually the electron configuration for the noble gas neon. And so what we're able to do is substitute the neon symbol in square brackets, and they represent the inner or core electrons of an atom. And we can write them out now as neon with the square brackets plus whatever outer electrons still exist. So for sodium in the top left there, we've got the neon core plus the 3s1 electron. So that's 10 electrons plus 1 electron is 11. Sodium has atomic number 11. Magnesium has the neon core of 10 electrons plus 2 extra electrons in the 3s subshell. So a total of 12. Magnesium is number 12 on the periodic table. Aluminium 13 has the core neon 10 electrons, 2 electrons in the 3s subshell and 1 electron in the 3p. So a total of 13 electrons, and aluminium is number 13 on the periodic table, and so forth. Now in the case of elements 19 and 20, that's potassium and calcium, we can see that the start 1s2, 2s2, 2p6, 3s2, 3p6 is actually the electron configuration for the next noble gas in the series, and that's argon. And so we can write condensed electron configurations for potassium and calcium by placing argon in square brackets and then just having the representing the outer shell electrons there. Now it's important that we can identify the outer shell electrons because they are the ones that are involved in bonding, and we'll get to that a little later on. So here now is a table of the condensed electron configurations for elements 1 through 30, and we can see that we've got the first noble gas, helium in square brackets, followed by the outer shell electrons for those first 10 electrons there. Then we have neon in square brackets for elements 11 through to 18, and then you can see argon in square brackets as well. So we're up to element 30 now, and the electron configuration is not as long as it otherwise might be. These are the condensed electron configurations. We can go from elements 31 through to 60, and we can see that krypton is being used. That's the next noble gas in the series. And we can even see xenon is being used for those elements 55 through 60. We can look at the condensed electron configurations for elements 61 through to the last of the naturally occurring ones, uranium at 92. And again, we can see xenon being used in square brackets there, and then radon gets used for the last of the 6 naturally occurring elements there. If we refer back to bismuth at number 83, you can see there that's the condensed electron configuration, so much, much shorter than what it otherwise was. So it has the xenon core of electrons plus the 4f14, the 5d10, 6s2 and 6p3 as the outer shell electrons there. So knowing how to write electron configurations, and especially condensed versions of electron configurations, becomes important for later work in understanding chemical bonding and being able to identify which electrons are involved in bonding and which electrons aren't.